There is a stretch of ocean between the southern tip of South America and the northern edge of Antarctica that has no equivalent anywhere else on Earth. It is not simply rough water, not simply a dangerous crossing, not simply a place where storms are frequent and waves are large in the way that many parts of the open ocean are rough and dangerous and prone to storms. It is something categorically different, a body of water defined by the absence of the one thing that limits the ocean everywhere else on the planet. Everywhere else, the oceans are bounded. The continents interrupt the circulation of water, break the momentum of waves, force the great current systems into turns and reversals that dissipate their energy. The Drake Passage, at the gap of approximately 800 kilometers between Cape Horn at the southern tip of South America and the South Shetland Islands at the northern edge of the Antarctic Peninsula, is the only place on Earth where the ocean runs free. There is no land, there is nothing to stop the water. The wind that circles Antarctica without interruption. The roaring 40s, the furious 50s, the screaming 60s, names given to these latitudes by the sailors who suffered through them, drives the southern ocean around the continent in a perpetual westerly flow. And at the Drake Passage, all of that energy, accumulated over thousands of kilometers of unobstructed ocean fetch, is compressed into a single corridor and pushed through. Waves in the Drake Passage can reach 20 to 30 meters in height during major storms. Waves the height of a 10-story building, moving at the speed of a fast train, arriving in sequences that give the crew of a ship no time to recover between one impact and the next. Sailors who have crossed it call it the roughest sea on Earth. The ships that have sunk in it call it nothing at all. The geography that makes the Drake Passage what it is, the gap between the southern tip of South America and the Antarctic Peninsula, is itself a relatively recent geological creation measured on the scale of Earth's history. The Drake Passage opened approximately 30 to 40 million years ago, when the tectonic forces that drive the slow movement of Earth's plates separated the Antarctic Peninsula from South America and created the deep water gap that now exists between them. Before the passage opened, Antarctica was connected to South America as part of the ancient supercontinent Gondwana, and the ocean could not circulate around the pole. The circulation was interrupted. The thermal isolation of Antarctica was incomplete, and the continent was dramatically warmer than it is today, capable of supporting forests and river systems in the regions that are now buried under kilometers of ice sheet. When the Drake Passage opened and the Antarctic Circumpolar Current was established, the current that now flows through the passage and around the continent without interruption, Antarctica was thermally isolated from the warm water of the lower latitudes for the first time. The ice sheet began to form. Albedo increased as the white reflective ice replaced dark absorbing land. The global climate shifted toward the cooler conditions of the Cenozoic ice ages, and the planet began its transition to the world we inhabit today. The opening of the Drake Passage was not merely a geographical event. It was one of the pivotal moments in the climatic history of Earth, a reorganization of ocean circulation with consequences that extended to every latitude on the planet and that continue to shape global climate in ways that oceanographers are still working to fully understand. The Antarctic Circumpolar Current that flows through the Drake Passage is the largest ocean current on Earth. It carries approximately 130 to 150 million cubic meters of water per second, a figure so large that it defies ordinary comprehension, but can be made tangible by comparison. It is approximately 100 times the combined flow of all the rivers on Earth. The current flows eastward around Antarctica at speeds that vary but can exceed 2 knots in the passage itself, driven by the westerly winds that circle the continent and by the density differences between the cold Antarctic water and the warmer water to the north. The Drake Passage narrows this enormous current into a relatively confined channel, and the combination of the narrowing, the wind-driven surface waves, and the complex seafloor topography of the passage, which includes the Scotia Arc, a chain of underwater ridges and island arcs that deflect and concentrate the current's energy, creates the sea state that has made the passage famous and feared. The waves are not simply large, they are chaotic. They arrive from multiple directions simultaneously, the product of winds and currents that do not behave in the orderly patterns of enclosed ocean basins. And the combined effect is a surface that heaves and falls and breaks in sequences that defy the predictive experience of sailors accustomed to the North Atlantic or the North Pacific or the Mediterranean. In the Drake Passage, the pattern of wave energy is not a steady procession of swells. It is a superposition of multiple swell trains arriving from different directions at different periods, intersecting to create rogue wave conditions in which waves of exceptional height and steepness can arise with very little warning, even when the average sea state is already extreme. The history of the Drake Passage in human exploration is a history of fear and hardship and loss accumulated over 5 centuries of sailing ships attempting to round the southern tip of South America. Before the Drake Passage was recognized as a navigable open water route, sailors rounding the tip of South America had to navigate the Strait of Magellan, the narrow and treacherous channel through the island labyrinth of Tierra del Fuego that Ferdinand Magellan first navigated in 1520. The Strait of Magellan was itself so dangerous, so narrow, so subject to sudden violent winds that sailors called it the place where you chose your death. The slow grinding passage through the islands or the open ocean attempt to the south. Francis Drake, the English privateer, after whom the passage is informally named, had his ship blown far south in 1578 after rounding the Magellan Strait. And his observations of the open water to the south of Cape Horn established for European navigators the existence of a route around the continent without the terrors of the strait. The passage that bears his name became the preferred route for sailing ships from the late 16th century onward, despite its ferocity, because the Strait of Magellan was considered even more dangerous. Sailors rounding Cape Horn acquired the right to wear a gold earring, a distinction that marked them as men who had survived the roughest passage on Earth. The ones who did not survive left nothing but accounts in other men's logs of ships that disappeared, hulls that broke, crews that were swept overboard by waves that came without warning in the darkness and left nothing to mark their passage. The oceanographic complexity of the Drake Passage is not limited to its surface conditions. The seafloor of the passage is one of the most geologically active and topographically complex regions of the ocean floor anywhere on the planet. The Scotia Arc, The curved chain of underwater ridges, seamounts, and island arcs that extends from the southern tip of South America to the Antarctic Peninsula is the product of the tectonic forces that created and continue to modify the boundary between the South American and Scotia tectonic plates. The Drake Passage sits at a junction of multiple tectonic systems, and the seafloor is characterized by deep trenches, abrupt ridges, and active volcanic features whose surface expression includes the South Sandwich Islands, a chain of active volcanic islands at the eastern end of the Scotia Arc, whose submarine calderas and hydrothermal vent systems have only recently begun to be systematically studied. The depth of the Drake Passage varies from over 5,000 meters in the central abyssal plain to less than 1,000 meters over the shallow ridges of the Scotia Arc. And these depth variations have significant effects on the current behavior and on the wave patterns at the surface. Where the current encounters a shallow ridge, it accelerates and its surface expression intensifies, producing localized zones of even more extreme sea conditions than the passage average. The interaction between the fast-moving Antarctic Circumpolar Current and the complex underwater topography of the Scotia Arc also drives intense vertical mixing, turbulence that extends from the surface to the seafloor in some locations, and that brings cold, nutrient-rich deep water upward in quantities that have significant consequences for the biological productivity of the passage and the broader Southern Ocean. The biology of the Drake Passage is as extraordinary as its physics. The enormous flow of cold, nutrient-rich Antarctic water through the passage and the upwelling that the current drives at the convergent zones where it meets warmer sub-Antarctic water creates one of the most biologically productive regions of the Southern Ocean. Antarctic krill, the small crustaceans that form the foundation of the Southern Ocean food web, are present in the Drake Passage in enormous concentrations, drawn by the phytoplankton blooms that the nutrient upwelling supports. These blooms, driven by the iron and phosphorus and nitrate that the upwelling brings from the deep, color the surface water green during the austral summer and produce the organic carbon that sustains the entire Southern Ocean food web from the smallest zooplankton to the largest whales. The passage is a major migration corridor and feeding ground for Antarctic fur, seals, leopard seals, and the multiple species of whale that feed in Southern Ocean waters. Humpback whales, fin whales, blue whales, minke whales, moving between the sub-Antarctic feeding grounds and the Antarctic continental shelf, or the albatrosses and petrels and other seabirds that spend most of their lives over the open Southern Ocean, use the Drake Passage as a regular transit corridor. The powerful westerly winds that make the passage so dangerous for ships, providing the lift and the speed that makes long-distance soaring flight possible for birds whose wing loading and soaring adaptations are calibrated to exactly these conditions. The wandering albatross, the largest flying bird on Earth with a wingspan reaching 3.5 meters, spends years at sea without landing, riding the winds of the Drake Passage and the broader Southern Ocean in a continuous circumnavigation of the Antarctic, returning to land only to breed. It has been estimated that a wandering albatross covers more than 100,000 kilometers in a single year. And the wind energy of the Drake Passage is the fuel on which that extraordinary journey runs. The Drake Passage in the modern era is no longer the feared barrier it was in the age of sail, but it is not tame. Research vessels and cruise ships now regularly cross it as part of Antarctic expeditions, and the crossing is considered a rite of passage for Antarctic scientists and tourists. A 2-day transit of genuinely violent ocean that separates the temperate world from the continent of ice. The passage can be encountered in 2 fundamentally different conditions that Antarctic travelers recognize by the names the Drake Lake and the Drake Shake. Drake Lake describes the rare condition in which the passage is relatively calm. Winds below gale force, waves of only 3 to 5 meters. A crossing that is rough by the standards of ordinary ocean travel, but manageable and even pleasant. Drake Shake describes the more common condition. Winds above gale force, waves of 8 to 15 meters or more. The ship rolling 30 degrees or more from vertical, all loose objects on board secured or broken. Crew and passengers confined to their bunks or gripping handholds, and the constant deep structural groan of a steel ship flexing under stresses that are at the design limit of its construction. The distinction between Drake Lake and Drake Shake is entirely at the discretion of the Southern Ocean, and ships that depart in lake conditions may find themselves in shake conditions within hours, as the notoriously volatile weather systems of the high southern latitudes rotate through the passage. The scientific study of the Drake Passage has accelerated dramatically in the past 4 decades, as the importance of the Antarctic Circumpolar Current to global ocean circulation and to the global climate system has become understood. The Drake Passage is the key measurement point for the Antarctic Circumpolar Current, the place where the entire flow of the current can be measured in a single transect from one side to the other, rather than attempting to measure a current circling an entire continent. Long-term current monitoring systems, moored instruments, seafloor pressure gauges, and acoustic Doppler current profilers have been deployed across the passage, measuring the volume, velocity, and water mass properties of the current at intervals sufficient to track the slow decadal changes in circulation driven by changing winds and changing ocean temperatures. The Drake Passage is also a critical site for studying the exchange of gases between the ocean and the atmosphere. The Southern Ocean is one of the most important regions for carbon dioxide uptake by the ocean, and the Drake Passage, where deep water upwells to the surface and exchanges gases with the atmosphere before sinking again in the cold, dense water formation processes of the Weddell Sea, is central to that exchange. Researchers have found that the rate of carbon dioxide uptake in the Southern Ocean has varied significantly over recent decades, responding to changes in wind patterns and ocean temperatures that are themselves the products of the larger climate system. And understanding these variations requires sustained observation in the Drake Passage over timescales that have been difficult to achieve, given the extreme conditions that the passage imposes on every instrument and every ship that attempts to work there. The passage is simultaneously the most important measurement site and the most difficult measurement site in the global ocean. What the Drake Passage ultimately is, at its deepest level, is a reminder that the ocean is not background. It is not scenery. It is not the space between the places where things happen. The Drake Passage is where the full force of what an uncontained ocean can be becomes visible, where the scale of water and wind and the absence of land reveals the ocean as the primary physical system of the planet, the thing that regulates temperature and distributes heat and drives the global circulation of both water and atmosphere, the thing that made the world habitable and continues to maintain the conditions in which life on the land is possible. The roughest sea on Earth is rough not because of some exceptional local catastrophe, but because of a simple absence. The absence of land in a belt of latitude that circles the entire planet. The absence of anything to slow the wind or interrupt the waves or break the momentum of a current that carries 100 times the water of all the rivers on Earth. The sailors who gave these latitudes their names, the roaring 40s, the furious 50s, the screaming 60s, were not indulging in poetic exaggeration. They were describing, with the precision of people whose lives depended on accuracy, the character of a system that operates at a scale beyond what the human body can easily absorb, and beyond what human engineering, even modern engineering, can entirely dismiss. The Drake Passage has not been domesticated. It has been crossed more safely and more reliably as ships have become stronger and navigation has become more precise. But the water has not changed, and the wind has not changed, and the waves have not changed, and every crossing is still, at some level, a negotiation with a force that is indifferent to the outcome. In the Drake Passage, the ocean is showing what it is when nothing gets in its way. The 800 kilometers between Cape Horn and Antarctica is not a dangerous place. It is a clear place. It is the only place on the planet where you can see the ocean whole.